For about a year now, we've been doing little mini updates, astro updates before many of the talks, and this is sort of becoming a series now with the gravitational waves, since gravitational wave astronomy is new and it's here and it's coming up with all sorts of new discoveries for us. So we're going to continue on with the fourth signal detected. It tells us some new things about neutron stars. So to recap from an earlier update, this signal came in August 17, 2017, 8:41 a.m. LIGO detectors. And this is a 100-second long signal, much longer than the black hole mergers that we'd had before, but a lot weaker. So the signal is kind of seen right in there. I don't see it there, but the experts are happy. This was...
There wasn't one on
There wasn't one, okay.
And that was critical in figuring out which part of the sky it was in.
Thank you, all right. And they were very fortunate to find it optically. This is NGC 4993, galaxy 130 million light years away. And telescopes swung into action, observing the light curve and the decay of this light, and we had the data from the gravitational waves that arrived. These neutron stars collapsed into a black hole, but they did some interesting things before that happened. We didn't really know how big a neutron star could be. A neutron star is basically a gigantic, a mile or a few mile long or diameter atomic nucleus. It's a whole bunch of neutrons jammed together. And we were pretty sure they couldn't be greater than about 2.5 solar masses. At that point, the core would be so dense that the speed of sound would exceed the speed of light. So, don't want to do that. So. But in the wild, the largest neutron star we found was just barely over 2 solar masses. So how big could they be, and how good is our understanding of quantum mechanics to predict when the collapse to a black hole occurs? So 4 teams worked on this, and it was very obvious that these 2 neutron stars that merged did not immediately form a black hole. You had a very rapidly spinning overweight neutron star. This rotational speed kept the neutron star up for a little bit of time. It was 2.73 solar masses at merger, and then it shed mass. And looking at the gamma ray burst and the afterglow, we saw about 0.1 to 0.2 solar masses of radioactive material spewed out. Just seconds later, it finished its collapse to a black hole. So looking at the data really closely, they figured that a neutron star that's spinning very rapidly could only exceed its maximum weight by about 18%. So that puts a maximum mass of a neutron star at about 2.2 solar masses. One team wants to refine it to 2.17 solar masses, but that's not completely agreed upon. So now we have a sort of a history of what happens when neutron stars merge. If they're heavier than the 2.2, they head right into a black hole. But if they're spinning rapidly enough, there's a little bit of time, like this example, where they will remain as an overweight neutron star before they shed that energy and mass and collapse. Below that, you can get a stable, non-rotating neutron star or slowly rotating one. So, an amazing amount of information you can squeeze out of just a little signal like this. And just wanted to give you a part 2 of our 4th signal. Any questions? All right, so we're going to switch over now, and I got to unplug here. Give you the mic. Dr. Vicky Hamilton is our speaker tonight. He's a staff scientist and acting Section manager of the Southwest Research Institute in Boulder. Received her PhD from Arizona State University. Has extensive experience with laboratory spectroscopy and planetary data analysis, and worked on a whole bunch of NASA. Could you hit number 3 on the black? Up above? And in the black, what's it, the, oh, sorry, all the way up on top shelf. We didn't practice that part, sorry. So she's working with OSIRIS-REx tonight, and she'll take it from here.
Okay, thank you very much. I take it everybody can hear me okay? I can hear myself, so I'm assuming you can all hear me too. All right, well, thank you very much for having me here. What I want to talk about is a mission I've been working on since about 2010. We are not to our destination yet, so what you're going to hear about is how this mission came to be, why NASA selected it, and what we're going to be doing when we get to our destination later this year. A little bit about me. I am not an astronomer. I'm actually a geologist by training, so I look at rocks. I'm interested in rocks and minerals in planets and on their surfaces and what that tells us about their history throughout time. I got involved with this mission by the invitation of the principal investigator, a gentleman by the name of Dante Loretta down at the University of Arizona. He and I were postdocs at Arizona State University at the same time, and I kind of commented to him that I had been looking at infrared spectra of Martian meteorites and studying Mars from spacecraft, and I was wondering what meteorites looked like in the infrared and what we could learn from that. And I think he remembered that, and when they came up with this mission and they wanted to fly an infrared spectrometer, he called me, and so that's how I got to be where I am today. My earlier life, I actually graduated from high school out in Aurora at Smoky Hill High School. I went away for college and grad school, and now we're back living in Boulder, working at Southwest Research Institute, which is basically an applied R&D company. Planetary or space science is only one thing the company does. It does everything from automotive engineering to fire and ballistics testing to applied chemistry. We have a division that handles contracts for the Nuclear Regulatory Agency out at Yucca Mountain. So the company does a huge amount of applied science in addition to the kind of stuff I'm going to talk about tonight. So here's a brief outline of what we're going to go over. I'm going to tell you what OSIRIS-REx is, where that name comes from. I'm going to talk about a set of meteorites called carbonaceous chondrites, what those are, why they're significant, why we want to understand more about them. I'll talk about what are the really broad science questions we want to answer in general, and then how this particular mission is implemented in a way to start to address some of those questions. I'll spend some time talking about how we chose that an asteroid by the name of Bennu would be the target for this mission. And then I'll talk briefly about how we're actually going to study that asteroid with the OSIRIS-REx spacecraft and the instruments that are on it, as well as how we're going to collect a sample and bring it back to the Earth. And then I'm going to close with some actual data from the spacecraft that we collected late last year when we passed by the Earth and had an opportunity to actually take a look at it with our science instruments. So OSIRIS-REx, like many things NASA, is actually an acronym. It stands for something other than just OSIRIS-REx. So it's O, S, I, R, I, S, and then the Rex. So the first part here is origins. So the ultimate and overriding goal of this mission is to go to an asteroid, collect a sample, and bring it back to Earth where we can study it in laboratories. Specifically, what we want to bring back is a pristine sample of carbonaceous asteroid regolith. So what that means, there's some jargon in here. Carbonaceous means kind of what it exactly sounds like, carbon-bearing material. Carbon is obviously something critical. It's a critical component of organic material life on Earth. Carbon does occur in the solar system, totally unrelated to life, but we want to understand carbon-bearing compounds from the early part of the solar system, which is what asteroids represent. Regolith is just a fancy geology word for the surface of the asteroid. On Earth, you might call it dirt or soil. We don't like to use that word on planetary surfaces because it often implies that there's an organic component. Things like dead leaves and stuff like that that are not on the surface of Mars or the Moon or an asteroid. The SI is for spectral interpretation. So we have 2 spectrometers on our spacecraft. I'll talk very briefly about those later. But the reason we have them there is twofold. One, to actually characterize the asteroid when we get there up close. This will help us understand what the asteroid is made out of. This is what I do scientifically. And we want to do that up close because right now the only information we have is from telescopic data from the Earth or from orbiting telescopes like Hubble or Spitzer. And those data, you don't really get a lot of resolution on the ground of what you're seeing. You get one piece of information sort of about the whole integrated object. It would be like looking at the Earth from Mars. You wouldn't really see necessarily like, oh, there's continents here and oceans there and the continents vary this way. So when we get close with a spacecraft, we have an opportunity to do a lot of spatial examination of what the asteroid is made out of. The reason that's valuable is not just to understand the asteroid itself, it helps us understand where our sample is going to come from on that asteroid, but it also allows us to then go back and compare to the telescopic data we got from Earth now and in the future, and help leverage that information for helping us understand all of the observations we make of asteroids throughout our solar system. The RI is for resource identification. There's a lot of interest now about using asteroids as resource materials for future human exploration of the solar system, or even as, mining targets, for example. And so we're going to talk about the potential for an object like Bennu to be a source of, in this particular case, primarily water. And that water is contained in minerals right now. It doesn't exist as water or ice on the surface. It's actually locked up in minerals. Security is another component of our mission. We want to measure something called the Yarkovsky effect. This is a scientific term that refers to how solar energy heats up the asteroid surface, and then when that energy is re-released, it actually pushes the asteroid a very, very tiny amount. A colleague of mine, I asked him, I said, well, how much of a push does this energy being emitted provide? And he said, hold out your hand. Okay. And he said, imagine 6 grapes. 6 grapes in your hand. The impetus that you can feel from that, that's the amount of push that an asteroid can get just from sunlight hitting the surface and then being re-emitted later. Why this matters is because Bennu is what is considered a potentially hazardous asteroid. What makes it potentially hazardous is that its orbit crosses the Earth's orbit, so it could conceivably impact the Earth. And until fairly recently, Bennu was considered the most potentially hazardous asteroid that we knew of. And so we want to understand how this Yarkovsky effect, or how the illumination of the sun, might actually change the orbit of the asteroid over time, either making it more potentially hazardous or less potentially hazardous. So we want to make measurements that help us really understand that effect and how, again, we can apply that to other asteroids that we know about. And then the last part, the REx, is Regolith Explorer. And so again, I just said regolith is just the rocks on the surface. So one of the things we'll be doing with cameras is documenting the surface of this asteroid, not just across its entire face, but at the place where we pick up the sample at incredibly fine scales. We're going to have photographs of the surface of this asteroid down to sub-centimeter resolution. All right, one more word slide and then we'll start moving into some more visual slides. But one thing I want to talk about is what is a carbonaceous chondrite, because I said we're going to a carbonaceous asteroid. Carbonaceous chondrites are a specific type of stony meteorite. They don't have a lot of free metal in them. Maybe you've seen pictures of meteorites called pallasites. They're big metal sheets with big green crystals in them. They're beautiful. This is not that kind of meteorite. There are other meteorites that are irons that oftentimes you'll see a polished surface that's been etched and you see these beautiful interlocking metal grain patterns. That's not what we're talking about. What we're talking about is something that looks like a stone that you might just pick up outside in your backyard. But it's carbon enriched and it never underwent any kind of melting. And when I talk about parent body, all meteorites come from a parent body, and you can think of a parent body as simply being an asteroid. But there are many asteroids which may have come from a common parent body, so that's why we distinguish between parent bodies and actual individual asteroids. These meteorites were formed 4.567 billion years ago. They were formed in the solar nebula. They form by what a geologist would refer to as a sedimentary process. So you have particles of stuff that just come together and become glued together as rock. The chondrite part of carbonaceous chondrites refers to the fact that these rocks have things called chondrules in them. And chondrules are usually spherical. Things can happen to change that, but they start out spherical. And what they are is solidified droplets of magma, lava, basically, made out of silicon and oxygen as the primary components. So that's the kind of meteorite that is an analog to the asteroid that we're going to go visit. Most of these are what we call primitive meteorites. Not much has happened to them in the time since they were formed. However, some of them have been exposed to water, so their minerals have changed form, even if they have not changed chemistry. And some of them have actually been heated. And when you heat up rocks high enough above their melting point, they can recrystallize. And so we classify the meteorites based on some of these additional properties that we see in them. They do appear to come from a number of different parent bodies or different asteroids. But again, I mentioned the carbonaceous part, that's the organic compounds, and they also have a lot of water, in some cases up to 22% by weight. And again, that's locked up in minerals. So those are the kinds of materials we want to bring back. You might ask, well, we've got all these meteorites, why do we need to bring a sample back? Well, unfortunately, to get any meteorite into our hands and into a laboratory, that meteorite has to transit through our atmosphere. It lands on the surface of our planet. In doing those things, it becomes contaminated. It's contaminated by our atmosphere, our biosphere, our hydrosphere. Minerals start to alter in that environment almost immediately. Even if we see a meteor fall and we go get it the same day, there are visible signs of interaction with the Earth's environment. And so we want to go get a pristine piece of this material that we can protect, bring it back, and not have it exposed to our environment until we are able to open it up in a laboratory that is exceedingly clean. By the way, I should say, if you guys have questions, feel free to pop your hand up or just yell at me if I don't see you and ask, because I don't want to leave you behind on something that maybe I forgot to mention or you just don't understand. That's fine. Okay, so here's an example of a carbonaceous chondrite meteorite. This is a very famous one by the name of Allende. In meteorite speak, it's classified as a CV 3.2. That tells you something about how it's been altered. In this particular case, a 3.0 is essentially pristine. A 3.2 means it's been heated up very, very, very slightly sometime in its history. So this is an example of what one of the stones looks like after it falls. This dark area here is a fusion crust. So that is the surface of the meteorite that actually melts as the meteorite is transiting the Earth's atmosphere, and then it quenches or becomes solid again as soon as it gets to the Earth. If you were to cut into this and cut a slab of it, this is what it looks like. So now you've just taken a slice out of the rock and laid it down on a table. And these dark objects in here are called chondrules. They tend to be fairly round. The white objects are called calcium aluminum rich inclusions. They form about in the first 5 million years after the sun forms. They're some of the very earliest forming solids in our solar system. The chondrules that these chondrites are named of, these are these silicates that were magmas that crystallized. They form these beautiful spheres. This is a microscope view of this rock. Now imagine we've taken a slab out of the rock. Imagine I could cut this into a slab only 30 microns thick, okay? This is something geologists do all the time to look at rocks. We cut what are called thin sections. It's a 30 micron thick slice of rock. We mount it on a glass slide, and then we can look at it in a microscope. And that's what this is. The light being transmitted through the microscope has been polarized, so that's why you're seeing all these colors here. And what you're seeing is the outline of a chondrule here, there's another chondrule here, there's another one there, and then all the different little colors and shapes that you're seeing in here are crystals, primarily of a mineral called olivine. Does anybody have the birthstone peridot? It's usually a December birthday. It's a really pretty pale green gem quality mineral. This is the same mineral, if you're familiar with what that is. And so this 500 microns, that's half a millimeter. And so these are actually, you know, reasonably good sized objects. If they were little, you know, balls rolling around on a table, you'd be able to see them. So these are the kinds of materials that we're talking about. So they look like rocks, but they don't really quite look like rocks like what we're used to. So to get on kind of to the mission side of things, we always have to start with some fundamental driving questions that we're trying to answer before we can actually formulate an idea for a spacecraft mission. So some of our fundamental questions are, how did our solar system form? We know broad brush strokes, we know that there's a nebula, we know that dust and gas are condensing out of this nebula, we know that things are crystallizing and accreting and forming asteroids and planets, but there's a whole lot of detail that underlies all of that we really still don't understand. So we're always trying to ask more questions that help us address that question. We also want to know, what is the diversity of material that exists in the solar system? We have lots of different kinds of meteorites. Some we have many, many more of than others. There are some kinds of meteorites where we only have a handful of them, and we don't understand why we have so few of those relative to other ones. Is that some process of how they get to us? Is it some representation of how much of that material there was in the beginning? We don't know, so we want to understand the diversity of everything that's out there. Of course, we all want to know, how did life evolve in our solar system? How did we get here? We really have no idea how we got here, how that chemistry of that solar nebula turned into all of us sitting in this room. And so we want to understand what was occurring very, very early on in our solar system's history to help understand what happened between then and now. And then we have this question of whether or not asteroids bring life in the form of carbonaceous materials, or do they bring death in the form of impacts that are very dangerous, change climate, cause mass extinctions, things like that. The answer really is it's both. And so we kind of want to continue to understand them and their role in the solar system. It's easy to treat asteroids as old dead objects just sort of floating around, but they still have a role to play in our lives. So from those fundamental science questions, we start thinking about scientific objectives that you can actually accomplish with a mission. So the first science objective of the OSIRIS-REx mission is to actually map an asteroid and pick a place to go get a sample that we can bring back. So we have cameras that will actually take pictures of our asteroid and help us do that. Once we've picked that sample site, we want to document it very, very well. We want to be able to go back years from now and have enough data that helps us understand the context of that sample. If I hand you any random rock, and if you know enough about geology to identify what kind of a rock it is, you might say, oh, that's a lava, it came out of a volcano. But if I don't tell you where I found that rock, all you know is that there was a volcano and it produced this rock. You don't know anything more about the Earth because you don't know where that rock came from. If I tell you it came from Hawaii, then you can start to make more intelligent inferences about what that rock represents as opposed to a rock that came from Iceland. So we really want to have that documentation. Then we bring the sample back where we can analyze it in laboratories. Most of the sample that we return will be locked away in storage for future generations. but a decent fraction of it will also be distributed to scientists around the world for analysis in laboratories everywhere so that we can actually start to get back to some of those fundamental science questions. And then, as I mentioned, we want to ground truth observations made from telescopes. So we'll take the data we get from Bennu, and we will actually use that to kind of go back and fill out a scorecard of how much did we predict about Bennu that turned out to be true, how much did we predict about Bennu that maybe we end up realizing we didn't entirely understand as well as we might have thought we did. So again, that helps us with future observations of other targets. And then refining orbital deviations. This again is coming back to that concept I mentioned about the Yarkovsky effect and the influence of the sun on asteroid orbits over time. And so once we have very detailed information about Bennu, then the people who go off and study orbital dynamics can go back and refine their understanding of their field of inquiry. So those are the scientific objectives of our mission. We still have to make that happen. How do you do that? The way you do that is you come up with a series of scientific instruments that you want to carry to your asteroid, and you have to figure out what sensitivities they need. You have to figure out how you're going to build them, how they're going to get mounted on the spacecraft, and all kinds of details about the actual execution of a spaceflight mission. So we were selected in late 2010 by NASA to fly to an asteroid. And between that time and when we launched in September of 2016, we were in what we call the planning and fabrication stage. Oh, hey, that's me. I keep forgetting that picture's in there. So during all of this time, what you see is a lot of meetings going on, a lot of presentations to other scientists and engineers talking about, okay, how are we actually going to make all this happen? And we go through a bunch of reviews for NASA to make sure that we're not being too risky and that we actually know how to do what we're doing. And so this whole multi-year period is taken up with those kinds of activities. In September of 2016, we launched our spacecraft. We are currently in what is called the outbound cruise phase of the mission. So we are on our way, cruising to our target, but we have not yet gotten there. In early 2017, we did what was called a deep space maneuver that helps correct our trajectory to make sure that we're really going to get to Bennu instead of, missing it by a few miles. In very late 2017, September, we came back around the sun and passed by the Earth again, and we did what's called a gravity assist. And I'll talk and show you some images about what that is and why we needed to do it. And then later this year, we will conduct what's called an approach maneuver, which will actually slow the spacecraft down a bit so that we don't go zinging past Bennu, and so that we can catch up to it, slow down, match its orbit, and actually start to do our science. We will be doing operations or collecting science data at the asteroid through all of 2019. We have some backup time in our schedule in 2020 to make sure that we've collected all the data we need to collect, that we understand where we want to collect a sample, and that we understand how we're going to collect that sample with our spacecraft. After we do that, we will depart Bennu in early 2021, and then we have to spend another 2 years coming back to the Earth. This is something most spacecraft missions don't have to do. Most of them go to Mars, go to the Moon, go to Jupiter, Saturn, wherever, and they never come back. So we actually have this long 2-year period to happen again at the end of the mission, and then our sample capsule will come down in very late 2023, and then we finish the mission out with actual sample analysis on the Earth. So here's just a little diagram to show you kind of what we're talking about in spatial terms. So we've got the Sun and Earth and Mars here in the inner solar system. We have the main asteroid belt out here where everybody's nicely behaved and stays in their lane. And then out here we've got Jupiter. What we're worried about are these near-Earth asteroids, these blue circles that have these really wild orbits that don't stay within the main asteroid belt. These are the guys that actually have orbits that cross the orbit of the Earth and can potentially impact with us. So those are the ones we're curious about. Now, it would seem like there's hundreds of thousands of asteroids out there. How do you pick one to go visit? And so we're going to spend a couple slides talking about how you do that. I'm about to show you an animation here that will start in 1995 when we knew about 23,816 asteroids. What you see here is the sun in the center. The little arrow is pointing to the actual location of the Earth's orbit. And you can see these little speckles out here. These are the known asteroids in 1995. And as I start this animation, what you're going to see are detections flashing up. Those white flashes are discoveries of new asteroids. As time goes by, we're in 1999 now. Red ones have been assigned as Earth crossing. So you don't see too many of those, but there's some creeping up in there. The yellow ones, again, there's not so many of those. Those are the ones that sort of approach the Earth. And then the green is everybody else. So the green is mostly the main belt asteroid population. But you can see that now as we get to 2008, we're starting to fill in and see a bunch more of those red and yellow ones in the inner solar system. By the time we get to 2010, we've gone from 83,000 known objects to over 500,000. And so now, 2010 is when we had to pick an asteroid. So we already know we can eliminate all the green ones. We're not interested in those. But we've still got a whole bunch in here to look through. So how do we actually choose? All right. We've already ascertained that we want a near-Earth asteroid, an asteroid whose orbit crosses the Earth's orbit and is potentially hazardous. We need an asteroid. So we started with those more than 500,000. When we go to the near-Earth population, there's only about 7,000 of those. Those red and orange, or sorry, red and yellow ones, that's about a 7,000 count of population. NEO here simply means near-Earth asteroid. So out of those 7,000, we need to find the ones that have orbits that make it favorable for us to go to it and come back. You have to carry all of your fuel with you when you go to some place in the solar system. There's no service stations with, gas out there. So any fuel that you're going to need to change your orbit, change your spacecraft path, you've got to carry it with you. So we wanted to find asteroids that had orbits that were just right for getting our spacecraft back to the Earth when we were done with our primary mission and being able to bring that sample back. When you look at those guys, you get down to about 192. So this is starting to sound not so horrible. Still, if I had to sit down and flip through 192 asteroids and be like, that one, what else can you use to help constrain the problem? All right, so asteroids come in all sizes, okay? They can be a couple of meters big. They can be hundreds of kilometers big. When they're very, very small, they tend to rotate very, very fast. And that means they fling off all their really fine material, like sand grains and small pebbles and things like that. So we need one that was big enough that that had not happened, because if all that's left is rock, we can't put that on our spacecraft and bring it back. We need particles that are about 1 centimeter in size, maybe 2 centimeters, all the way down to dust. So we needed a surface that would have that kind of material on it. So the criterion we used to define that was that we needed an asteroid bigger than 200 meters in size. So when you go from your 192 that have optimum orbits, now you come down to 26 that are bigger than 200 meters. You can almost do this on your hands and toes now. So we're really getting this problem constrained down nicely. And then finally, because of our science objectives, we want a target that's got water and organics in it, because we want to understand these questions of life and resources and things like that. Out of those 26, only 5 appear to be carbonaceous. Now you can actually make a choice. And we chose an asteroid called Bennu. So here is a view downward onto our solar system. So you can see the sun, the orbits of Mercury, Venus, and Earth in green. Bennu's orbit is here in blue, so you can see that it crosses the Earth, and then Mars is out here. If you look kind of from the side, this is what things look like. So Bennu's orbit is inclined with respect to the plane of the ecliptic. This is the only imaging kind of data that we have. It stutters there because it's loop. This is from the Arecibo Radar Observatory in Puerto Rico. This is a radar movie of Bennu. And this is what we call a shape model. So this is a numerical model based on the radar data of what we believe Bennu looks like. So for an asteroid, it's actually reasonably spherical looking-ish. It's got a retrograde spin, so its north pole actually points downward. It's just under 1/2 kilometer in diameter. So here, I want to find a better picture than this because I've never been to the pyramids. I don't know if anybody here has. I don't know how big the pyramids are. So anyway, but you know, it's not that big is the point here. The Earth day is 24 hours long. The Bennu day is 4.3 hours. So that's that small objects are spinning faster. That's what that is right there. But its year is actually longer than ours. It's about 437 days. The bulk density is actually very interesting. 1,200 kilograms per cubic meter is actually a very low density. The density of Earth rocks is about 3 times that, maybe a little tiny bit less than 3 times that. It's about 3.3 or 3,000 kilograms per cubic meter. So this is very underdense. The density of water would be 1,000. So we think this is actually not a solid object, but a collection of rubble that's being held together by gravitational forces. Albedo is a fancy word for how bright it is. This screen has a very low albedo. It's dark. It doesn't reflect a lot of light. The wall has a high albedo. It's very bright. A 4.5% albedo is extremely, extremely dark. This object is darker than a charcoal briquette. So it is very, very nearly black. I mentioned that Bennu is a potentially hazardous asteroid. Here's your actual hazard assessment. There's a 0.037% chance that this asteroid will hit the Earth sometime in this time frame. Not our problem, but somebody down the line, children, grandchildren, great-grandchildren are going to care about this. And then I mentioned before that the best analogs or the best meteorites that we know of that look like Bennu, or we think look like Bennu, this is going to be one of the things we ground truth, are carbonaceous chondrites that are classified in groups called CI and CM, which is beyond the need to know for this group. But the point is they contain carbon and volatiles like water. So that's where we're going. Here is what the spacecraft looks like. So here's a man for scale. He's 6 feet tall. This is the sampling arm next to him. The body of the spacecraft is here. This is our high gain antenna for communicating with Earth. The wings here are our solar panels, and our instruments and sample return are on the other decks, and we'll get a better view of that in a minute. Here's some sort of dimensions if you're curious about those. We have 5 science instruments. I mentioned that we have 2 spectrometers, one that covers visible to near infrared wavelengths from about 0.4 microns to 4.2 microns, if you're familiar with those, with what that means. Our other spectrometer covers from about 5.5 to 50 plus a little microns, so what we call the thermal infrared or heat energy. We have cameras. We have a suite of 3 cameras, one that's designed basically like a telescope. It's the first thing that will see Bennu a million kilometers away. We have another one for up-close mapping of Bennu, and then we have a 3rd camera that will be able to focus in that sort of 15-foot range between the spacecraft and the surface when we actually do the sampling. So we needed to have different cameras for the different distances that we need to be able to see at. We have a laser altimeter. So it's an instrument that shoots a laser literally at the surface, and it looks at the timing of the reflected light. So that tells you how far away the surface is, so you can make a map of the topography of the surface. We have an X-ray experiment that was designed and built by students at Harvard and MIT. And so that's the 5 instrument suite that we have. That will give us some chemical information. we have what we call the TAG-SAM, which is short for Touch and Go Sample Acquisition Mechanism. Nobody wants to say that in meetings 5 times a day. So we call it TAG-SAM. TAG-SAM is the little disc that sits down here. You'll see pictures of that and how it works in some of the movies I'll show later. And then we have a sample return capsule. So we're going to collect a sample here, but then it's going to get put into a capsule on the spacecraft, and that will get ejected from the spacecraft when we come back to Earth, and that's how we get our sample back.
Does that mechanism grab a finite amount of material multiple times?
You'll see a video of how it actually functions, but basically it's a container and we fire nitrogen gas into the surface. It stirs up that stuff and forces it into the sampling head, and then we just back away. So there's no actual manipulation of the rocks. So these are those instruments I just described. For those of you remembering electromagnetic spectrum, here we have our high energy gamma rays and X-rays, the ultraviolet, the tiny little slice of the spectrum that our eyes can see. And then we have the infrared, microwave, and radio frequencies. And so we've got our camera system that works in the visible. We've got the X-ray chemistry instrument, the 2 spectrometers for determining minerals. We have the laser altimeter that operates at a very specific frequency. And then our telecom system for the spacecraft can actually also be used to do some scientific analysis as well. And this is how they're all mounted onto the spacecraft. So here's that sampling arm again. Here's the sampling head. And then our spectrometers are mounted here. The cameras for the camera system are all of these things: Polycam, Mapcam, Samcam. And then Rexus is the student experiment back here, and the laser altimeter is here. This is our sample return capsule sitting up on top there. All right, so now we're going to talk about the launch, and I'm going to show you what I think is a really well done movie about the launch. I believe it was September 6th or 8th, I can never remember which one, of 2016. We were down at Cape Kennedy, had a beautiful, beautiful evening launch. I think the launch was around 7 p.m. Gorgeous skies, gorgeous weather, beautiful day. This is a photograph that somebody on the team had a relative who was on a commercial airliner at the time of our launch and took this picture of the launch out their window. And then these are obviously ground shots. This one is one of my favorite ones because you can actually see that the main engine nozzles are vectored off of normal because we have one solid rocket booster. Usually you always have 2 or 3 and you can space them around the main engine evenly. But when you only have one, you can't do that. So to counteract the force of that solid rocket booster, you have to actually vector the nozzle in the main engine, and you can actually see that in that photograph, which I always think is really cool.
Why didn't you guys have one in the front?
Because we didn't need it. You only want to buy as much rocket fuel as you need to get off the ground and absolutely no more. So that's why. All right, do we have our sound? Sorry, here, I'll just pause it for a second. All right, let's
Reset the sound.
There we go. Hang on. Come back. There. There we go. So the spacecraft sits up in this fairing up here. There's our solid rocket booster. This whole system only moves at a couple miles an hour, so it takes a couple of hours for them to get from the facility out to the launch pad. ULA advertising.
Well, they are local.
Yeah.
Status check to proceed with terminal count. Atlas systems propulsion. Go. Hydraulics. Go. OSIRIS-REx. 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx. Its 7-year mission to boldly go to the Asteroid Bennu and back.
If you ever have an opportunity to go see a spacecraft launch, I highly recommend it. You can feel it in your bones from miles away. It's an amazing experience. And that's the last we ever saw of OSIRIS-REx. Okay. All right, so I showed you a graphic earlier, and I'm showing it again just to give you a sense of what I'm about to talk about. So we've got the sun, we've got the Earth's orbit in the plane of the ecliptic, but Bennu's orbit is inclined. And so when we launch from the Earth, we launch into the Earth's orbital plane. So we needed to find a way to get into Bennu's orbital plane, and the way we do that is with something called a gravitational assist. So basically, we fly around the sun, we catch back up to the Earth, and then we go underneath it, fly past it, and that gives us a slingshot effect that actually puts us into the orbit of Bennu. And so this is showing you, we launched from the Earth. OSIRIS-REx went actually inside the orbit of Bennu briefly. It will appear as though it's going to catch up to Bennu, but it doesn't quite. And in a moment, the perspective here will change from looking down on the sun to now we'll zoom around so that you can see everything from the side. So there's Bennu going off up at an angle. The Earth is coming along in the plane, and now OSIRIS-REx swings past the Earth and it gets put into the Bennu-like orbital inclination. And so now we have to spend, we did that last fall, and so now we're on our way to Bennu, and we're actually going to be able to catch up to it to do our science. Catching up, catching up. Earth will continue on its path. And then here we are, and now we can start doing our science. Now, one of the other things we did when we did that Earth Gravity Assist was we actually took data with our science instruments. So the cameras took pictures of the Earth, the spectrometers scanned back and forth across the Earth to collect spectral data. So we don't take pictures with those instruments, we collect these sort of squiggly line things. And we use those to help us ensure that the instruments are performing the way we expected them to once they've gone through that very vigorous activity of launch. They're all designed to survive that. We do a lot of testing to make sure they do. But it's always nice to have an actual scientific target to look at before you actually get to your destination. And so we actually use this opportunity to do that. And it was a lot of fun because you've got this 2-year cruise phase, and it's really nice to actually get some data midway through that process. So here was the very first image that we got back from our spacecraft of our home planet. So this is an image of the Earth taken by our camera system, OCAMs. And so you can see that we were pretty much looking at the Pacific Ocean. Here's Baja and coast of California and Mexico. Here's Asia. Here's the eastern portion of Australia, and then you've got New Zealand, and can't see Hawaii quite. But what you're flipping back and forth with is colors that indicate the presence of vegetation on our planet. We're not going to use this at Bennu, of course, but it was kind of a fun thing to be able to do on the Earth. Here's a picture of the moon that we collected 3 days after. And this is a lot of the backside of the moon, actually, not the part we usually see. Here's an image showing the Earth and the Moon in the same image. So this is the actual distance and scale of the two objects. And then from our visible and infrared spectrometer, there's a little tiny yellow circle there. That's the location of where this black line was measured. So if you were looking at an object that had nothing of interest on it, all you would see is this sort of reference curve, okay, this red line. But because our atmosphere has a ton of water in it, we've got CO2, and then there's also the water on the surface of the ocean, you actually have deviations from that perfect curve where molecules are interacting with light and causing absorptions. And so the absorptions are these deviations down from the red curve. And we know very, very well which ones are related to which molecules. And so we've got them labeled here. Some of these are due to water vapor in the atmosphere. Many of them are. We've got features due to actual oxygen, and we've got some features due to carbon dioxide.
Excuse me, what's the resolution on that instrument?
It's got a 4 milliradian field of view. So resolution obviously depends on how far away you are.
Resolution.
Oh, spectral resolution. Between 0.4 and I think it's roughly 2.5. This portion of the spectrum, it's 2 nanometers. Beyond here out to 4, it's 5 nanometers.
About an R200, R300, R400?
I don't think of it in our values. I'd have to look. I'm sorry. I know SNR is 50 or better. And then our thermal emission spectrometer that looks at the much longer wavelengths, here's a series of 8 spectra that are represented by these yellow circles. Our field of view is 8 milliradians, so it's much bigger because we need to collect more light. A reference curve here in red is shown for the ocean surface temperature of about 13 degrees Celsius. And then a blue reference curve is shown for the temperature of our stratosphere, which is about minus 39 Celsius. So again, these reference curves are what you would get if our atmosphere and our planet had nothing on them or nothing in them or around them. But all these deviations that you see are attributable again to various things in our atmosphere. So we actually have a two-humped absorption here due to methane in our atmosphere. That's a sure sign of life on this particular planet. We have this big absorption here due to ozone in our atmosphere. We have this enormous absorption here due to carbon dioxide. If you were to look at a spectrum like this of Mars, you would see this same feature here because Mars' atmosphere is almost pure carbon dioxide. A lot of these little tiny jaggies here you might think are noise. A lot of them are actually due to water vapor in the atmosphere. So these are not the same resolution in terms of the distance between points along here as what Earth satellites measure. But Earth satellites that are interested in weather and climate measure in actually this part of the spectrum. We can't actually see through here usually. So those are some of the data that we've actually already gotten from our mission. But here is sort of the outline of our mission. Unlike a mission to Mars, for example, which is what I did before I was working on this, you'd go to Mars, you'd go into orbit, and you would just continue to collect data continuously all the time. But with this mission, we actually have a whole bunch of different kinds of experiments we need to do from different locations around the asteroid, and different kinds of science that mean that we need to be in different places. So we will approach the asteroid later this year. We expect to get our first light, not first images exactly, but, well, there'll be images, but first little dots of light later in August, and then we'll get our first data from the spectrometers in early November. So you'll be hearing about that going into the holiday season from NASA. And then we have all these individual mission phases that are each designed to accomplish a different kind of science. And ultimately, we use all those data to help us decide where do we actually want to go. So we have a decision point where we have to pick our primary and our backup sites. And then we have to actually rehearse the process of getting the sample. We've never done this before. We've certainly never done it with this spacecraft before. So everybody needs to get familiar with actually flying the spacecraft close up to an object that you're going to touch but not land on. And you've got to be able to back away from it and not lose your spacecraft in the process. So once we've gone through the whole rehearsal and sample acquisition process, then we actually have a departure date set for 2021. So that is the outline of the mission that is all still yet to come. And this will show you a little bit more about sort of how we actually do the sampling. There's no sound for this video, so I'll just sort of narrate as we go. But we will fly up close to Bennu. We will get within a couple kilometers of it. And we will go to a distance of about 1 kilometer to do some mapping. So we'll take pictures. We will scan back and forth with the spectrometers to collect data. We'll be targeting specific locations. And then we actually have to match the rotation rate of the asteroid so that as we approach it, it looks like it's not moving underneath us, because you don't want it spinning while you're trying to approach it and sample it. So the sampling arm pops out. Some of us jokingly refer to this as the Fram air filter, if you're old enough to know what a Fram air filter is. It looks a lot like that. The arm is sprung, so it's not rigid, but we will be coming down towards Bennu. We will contact the surface, and then what you'll see, this is actual flight footage from an airborne test flight. So the gas disrupts the surface, which then goes into the sides of this container, and then it pulls back away. The whole spacecraft backs away from Bennu, and then we actually will store the sample in the capsule. These are some of the cameras and instruments down here. Close it up, and then we head back to Earth.
So that's a one-shot operation then?
We actually have 3, so I'll talk about that in a minute. So we come back past the Earth, we send the capsule to the Earth, and then we immediately have to do a burn to prevent OSIRIS-REx from impacting the Earth. The capsule comes down, deploys parachutes. It will land in the Utah Test and Training Facility in the desert, where we have a science team who will go out and collect it. This is the same capsule design as was used on the Stardust mission, which was a comet sample mission a few years back. What you're seeing is footage of the Stardust capsule recovery, and this is the capsule being opened at Johnson Space Center. This is again back to footage of our test data set from the airplane flights. So we have a requirement to collect about 60 grams of material. You can hold that in your hand. With those test cases that we've run, we've collected as much as 2 kilograms, or about a little over 4 pounds of material. So we're of course hoping that we will get a lot of that material back, not just the 60 grams, but the 60 grams is what we're required to bring back for our mission design. And then in terms of the answer to your question about do you get only 1 shot, you actually get 3 potentially. So we've got 3 gas canisters. So if we pick a site, we have all kinds of data that we collect to make sure that the site meets a bunch of requirements that, for example, the materials at the site are small enough that they will go into the throat of the sample collector. They've got to be small enough to do that. Wouldn't do us any good to put it down on a big rock that won't go in there. And then we have all kinds of requirements about what the surface topography of Bennu can be like there, because we don't want to endanger the spacecraft by having some big rock sticking out or something that we might hit. But if for some reason we pick a site, we think it meets all our criteria, we go there, we do the first canister of gas, one of the things that we do before we stow the sample while the arm is still extended is we spin the spacecraft to get moment of inertia measurements, and that helps us discern how much material we've actually collected. If we can't discern that we've collected any material, Then we have a decision to make about, do we go back and use another canister and try to get more? If we do that, do we go to the same place? Maybe depends on what we learn in the process about what might have gone wrong. We might go to our backup site at that point. But hopefully we will only need to do it once. We'll get the mass we need, and then we'll button it up and come home. So. All right, and I do believe that is the last slide I had. I wanted to put these up there so that if you're interested in understanding more about the mission, we have a website. Our principal investigator, the scientist who leads the mission, has his own website where he records his own perspective on the mission. We have Facebook, Twitter, YouTube, and Instagram as well. So hopefully you guys will keep up with what we're doing, and when we get data later this year, I'd be happy to come back and tell you more about that. But in the meantime, I'm happy to answer any questions you still have.
Does the sample stay under vacuum?
No, it does not, and it does not stay cryogenically maintained.
Okay.
Well, it's under vacuum to the degree that it's in space,
Right.
but we don't have an active vacuum system.
Okay.
So, yeah.
Because of the density, is it affected by the Earth's atmosphere when you bring it into the Earth's atmosphere by the gravity and the concentration of it?
The sample, you mean? So the sample will be fully enclosed within that capsule.
Okay.
And then we will only open it once it's at Johnson Space Center in an extremely clean environment. And then they may, in fact, I don't know exactly, for this mission, the protocol may be to open it, for example, in a nitrogen environment. So it may be in some sort of a box where they open it. I'm actually not sure. That's a good question about that part. So, but yeah, the idea is that we keep it protected from the Earth's environment all the way until we get to the lab where we can control things very carefully. One of the things that we've done all the way through the construction of the spacecraft was we had little witness samples all through the facilities. So for example, our spacecraft was actually put together, built down at Lockheed Martin in Littleton. And so when you go into the high bay down there where they're actually building the spacecraft, they had little sample places all through that high bay, and they had a contamination control person whose job it was, like once a week, to run out there and actually make measurements of what was on those little pieces of sticky tape and papers and all that sort of thing. They collect some of them and put out new ones, and all of that is actually part of our science too, because we had very strict requirements about not putting organic material in the vicinity of the spacecraft, because we're trying to get pristine organic material. So we don't use nylon on this spacecraft, for example. You have to be careful about lubricants and glues that might have organic material in them, and so anything that had that, we had to archive it. We had to provide samples of it so that if we somehow contaminate something, we can actually go back and trace back what the spacecraft was exposed to and where. So that's, we really are worried about those kinds of contaminants, and so it will be kept as sealed as possible, as long as possible.
This might be kind of a naive question, but is there any concern about radioactivity of the material?
No, there really isn't. For these kinds of rocks, we know from the meteorites that these aren't highly radioactive materials. The most radioactive rocks we have on Earth are things that, really are like uranium bearing and things like that. And these kinds of rocks just don't have that kind of chemistry. It's not a bad question. Anything else? Okay, well, thank you very much for your time. I appreciate your all coming out.